Hey guys, I wanted to give a homework correction. Actually, I was kind of like describing how to do this homework problem, and I'm giving you like a generic excuse, but it's actually the way I've been doing it is entirely wrong, and I feel like I need to correct it. I've been kind of giving you the intentional wrong answer because I think this is what whoever wrote this problem, whoever wrote all these homework sets, I think when they wrote this problem, this is what they intended. This is on number 3, homework 7. It's the one with natural logs, and I'm not a big fan of this one, at least for this class at the moment, because I can't tell exactly how technical they want you guys to get with some of this stuff. Typically when you're seeing these, so this isn't like a problem of set of 4, and when you see series and it says determine whether each series converges or diverges, if it converges, find its sum. And when you have to do a series of these, they shouldn't take you more than a few minutes. And you guys have seen from this homework that you have plenty of these to do. You have 4 in the first section, then you have a bunch more problems, then you have like 6 more in another section. You should be able to start looking at a series and get a feel for converge or diverge based off of all the tricks. So the problem with this guy that I've kind of been saying, I think what they wanted, what the writer of this problem wanted you guys to see, was to show that this was natural log of k minus natural log of k plus 1. And so here's an explanation. This is the incorrect explanation, and what I've kind of been telling you guys. Primarily just because we wanted to see some aspects of a telescoping series. Natural logs, remember, of course, when I have a natural log of a division, we can split it. Natural log of k minus natural log of k plus 1. And whenever I have a series that looks like some function of k minus another function of k plus 1, you want to start thinking about telescoping and recognizing these telescoping series. It's kind of one of the hardest things to do. The only other time we see telescoping series is when it's like a partial fractions looking thing. So I think what the writer wanted us to do, they wanted to try to plug in or throw in this hidden telescoping series that we might have using natural logs, but it's not correct. So let's kind of see what happens and what goes wrong. The incorrect reasoning is that we would have natural log of 1 minus natural log of 2 plus natural log of 3 minus natural log of 2 minus natural log of 3 plus natural log of 3 minus natural log of 4, etc., etc. And of course, the natural log of 2's will cancel, the natural log of 3's will cancel, the natural log of 4's will cancel. And this looks like everything should cancel and divide, and then we're just left with natural log of 1, which is 0. And our argument is, okay, maybe this whole thing, the terms are getting really, really small, and then they're just plus and minus, and they cancel in some way, shape, or form. This is bad logic. What's going bad here is the fact that even though I'm canceling every consecutive term, what's happening with each consecutive term? Each consecutive term is getting bigger. So it's, if we have a series that is 1 minus 2 plus 2 minus 3 plus 3, depending on how you group the terms, that could look like it converges, or it could look like it completely diverges. And so the proper tools to do to the one I just described, you guys don't quite have. But the key thing with the telescoping series is that we still need the individual terms to go to 0. In this case, the individual terms, at least written like this, they don't quite go to 0, but we're left with an infinity minus infinity. Here, this is the problem. If I try the divergence test, what happens as k goes to infinity? I'll get 1 over 1, or infinity over infinity, and it'll go to 1 over 1, and natural log of 1 is 0. So here the individual terms do go to 0. It's just hard to tell. Okay, well here the terms go to 0, so it could converge or diverge. Here the individual terms don't go to 0, but it's an infinity minus infinity. which is another indeterminate thing, another type of thing that tells us we need more work. And if we do this telescoping thing, I think this is what we originally wanted you guys to see from whoever wrote this problem, but it's not correct because the terms themselves don't go to 0. You can't quite necessarily conclude that all we're left is the first one, because we're adding and subtracting, infinity at the very end. It's plus infinity, minus infinity, plus infinity, minus infinity. And what's that going to do? It's kind of another ambiguous case when we get an infinity minus infinity. So to do this one properly, you actually need to do, I think the best way to do it would be to do the integral test. And I'm going to do it, and I'm going to skip through some of the parts primarily because doing an integral test on something like this, again, we want you guys to get used to doing these tests and kind of recognizing them, and the test should work out once you get the hang of it. It shouldn't take you more than a couple minutes. Once you nail the right test and know I should be able to identify it with this test and determine convergence or divergence, should just happen pretty quickly because you're going to have a lot of these to get through. And well, if we were to try to do this with an integral test, it ends up being like an integration by parts. And you got to do 2 integration by parts. And if you forget how to integrate natural logs, you got to do every step of the integration by parts. And if you're rough on that, there's just so many chances for mistakes. Let alone integration by parts is kind of the longest technique, I think. I think trig subs are even a little bit quicker, just making a quick substitution and finding antiderivatives. Whereas integration by parts, you got to keep track of each term, then do another integral after you rewrite it, So what's our integral test going to say? Our integral test says, well, if this integral converges, then this series will also converge, or at least this series, this integral in this series should converge or diverge simultaneously. And how the hell do we do this integral now? This is kind of another thing, like it's not quite immediate, but of course, since we did see the natural log trick, we can write it as natural log of x and split our integrals. Natural log of x plus 1. Okay, those look like a little more nice integrals, but this is what I was saying. You got to remember how to integrate natural logs, and you got to do it twice. So an integral test, we like the integral test, and it does come up with natural logs. So let me just kind of give a little aside for this problem, because I think problems like this have shown up on WebAssign or on your other homework assignments. When you have natural logs, you want to look for things like, whenever we have n natural log of n, what's the derivative of natural log of n? It's 1 over n. So in cases like this, or in cases like natural log of n over n, integral tests work really well for these guys. Or even if natural log of n, I could even square that natural log. Because as soon as I switch it to an integral test, it's something like 1 over x, natural log of x squared. And now integrating that's easy because we can do a quick u sub. U is natural log of x, dx then is that 1 over x. And the integral just kind of pops out pretty easily. So in general, you can try integral tests when these natural logs come up, but they work best whenever there's like a 1 over n accompanying it. When there's not a 1 over n, well, now we've got to integrate natural logs, and we've got to do integration by parts. I'm going to skip the integration by parts because we have done this integral a couple times. So if you remember it at least, you can save some time. The first one is going to be x, natural log of x minus x is the integral of natural log of x. Minus this one, because there's an x plus 1, you'll have an x plus 1 natural log of x plus 1 minus, and I'm just going to keep it as minus x. You could write it as minus the quantity x plus 1, excuse me, if you wanted to, but that plus 1 is just a plus a constant, so it's not going to change anything. So try this, either take a derivative of this guy and take a derivative of this guy to see if you get back here, or go through the integration by part steps yourselves. And I'm going to compute both of the limits of this whole function, because unfortunately what would happen if I put the limits here and here, we'd get another infinity minus infinity minus infinity plus infinity. And we get weird sums and differences of plus and minus infinities. So what I'm going to do is we want to recombine the logs and simplify it in such a way. Of course, we can put a t there and take the limit as t goes to infinity, or you can just think of it as infinity. What's going to happen when we recombine this? We'll have x natural log of x minus x. We will have minus x natural log of x plus 1. So I'm distributing these guys. We will have minus natural log of x plus 1. And then that minus will distribute, and we will have plus x, 1 to infinity. So combining our terms, the reason I wanted to factor that out is because I want to recombine these two logs here. So we will have x times natural log of x over x plus 1. Luckily, at least, this x and this x will cancel. And so with these two guys, all I did was factor out the x, natural log of x minus natural log of x plus 1. We then combine into this term, and then we have this extra natural log hanging out. And we want to evaluate from 1 to infinity. So the 1 doesn't matter, it'll give us a number. We really need to figure out, will this give us a finite number as we get to infinity? And what's the problem we are running into if I plug in infinity? I get infinity times 0. Natural log of 1 is what that's going to go to. So infinity times 0 minus infinity, another indeterminate form. You would have to deal with this infinity times 0, because infinity times 0 could go off to infinity, or it could be finite. And if it did go off to infinity, then we'd have infinity minus infinity, and we'd have to deal with that indeterminate form. So you're seeing how much kind of a mess this problem is to do properly. I'm going to get through a trick, and this is the type of trick that, you know, I don't quite expect you guys to come up with. You know, your guys' skills are still at, you know, being able to do basic integrals, basic logic arguments. What we can do is say minus x natural log of x plus 1 over x. So, right, this is just x plus 1 over x to the minus 1. I pulled out the minus 1 there. Why did I do that? Just to make a mathematical argument. Because now, what's happening when I plug in t? If I plug in infinity or really large numbers into this guy, it's going to be natural log of 101 over 100, which is slightly bigger than 1. And if it's slightly bigger than 1, natural log of that number is going to be positive, right? So this is a positive number. But again, I'm plugging in numbers getting close to infinity, which are positive numbers, and now I have that minus sign out here. That term's going to be negative. And what's happening with this term? It's going to be minus infinity. So I'm getting around the indeterminate forms by making this argument. This number, it's going to 0, but it's going to be a positive, going to 0 from the positive side, which means this whole quantity, minus x times natural log of x plus 1 over x, is always going to be a negative number. And any negative number, even if it's going to 0, or even if it's going to any finite number, or even if it's gonna go to an infinity, it'll actually go to a negative infinity. And which means I really have a negative number, whether it's minus a constant or minus infinity, minus another infinity. And so negative infinity minus infinity, or a negative constant minus infinity, both situations, it'll go to negative infinity specifically. So this will diverge. I hope that makes sense. If you want, think about those arguments again. Otherwise, to do it properly, if we wanted to use our Calc 1 techniques, when I take this limit to infinity, we're getting a minus infinity times 0 minus infinity, which is this weird, complicated indeterminate form. We would have to do a bunch of work to figure out what this limit is, because that's an indeterminate form. And then we potentially have the problem of an indeterminate form inside of a bigger indeterminate form, which requires even more work. And if you don't know how to just kind of reason through it and explain, it's going to be a lot of work. And the reasoning there that I kind of just gave isn't the type of thinking that we're really demanding out of you guys yet. I don't think it's fair. And it's certainly something like this will not be on an exam. Okay, so that's clarification on that problem. Hope it kind of makes sense if you guys want to watch this video. Otherwise, I'm not going to grade this one, because really I think we wanted you to kind of see a telescoping thing here, as I was kind of initially saying, but whoever wrote the problem wasn't, I don't think, thinking this problem all the way through in terms of the difficulty and how to do it properly for a Calc 2 student. All right, so I'll put this on YouTube, and if you guys want to catch up, feel free.